When multiplying radicals, we wanted to look at multiplying radicand by radicand and coefficient by coefficient. So if we take a look at the very first example, root 3 times root 7, we simply multiply those radicands together to come up with square root of 21. Looking at root 21, 21 does not have any perfect square factors, and therefore it is considered simplified. Looking at example number 2, 2 root 3 times 5 root 7, multiplying the coefficients, 2 times 5 is 10, root 3 times root 7 is root 21. And again, simplified because root 21 does not have any perfect square factors. When multiplying example number 3, root 10 times root 15, again, 10 times 15 gives us root 150, but this time we can see that 150 does have a perfect square factor of 25. So we can break that down to root 25 times root 6, and root 25 is the same as 5, so we then have 5 root 6. Now taking a look at example number 4, we have a couple of ways to handle this. First off, we could figure out what 24 times 162 is, but then the number becomes very, very large to find any perfect square factors becomes difficult. So it's a lot easier to simplify ahead of time. So root 24 we know is the same as root 4 times root 6. Root 162 is the same as root 81 times root 2. Simplified then, we have 2 root 6 times 9 root 2. Multiplying the coefficients, 2 times 9 is 18, and root 6 times root 2 is root 12. So normally we would think that we'd be done, except of course looking at our radicand, we can see that there's still a perfect square factor of 4. So 18 times root 4 times root 3 is the same as 18 times 2 times root 3, or simply 36 root 3. Remember to check your work. We can enter root 24 times root 162 into the calculator and come up with an approximate decimal value, and again enter in our simplified product of those two radicals, 36 root 3, to also check if we come up with the same equivalent decimal approximation. Looking at example 5, we can distribute just as you would when working with polynomials. So 3 times root 2 is simply 3 root 2, and 3 times 5 root 7 is positive 15 root 7. Both of my radicands are such that they do not have perfect square factors, so they are simplified. Looking at example 6, same thing, we'll be distributing, so 3 root 5 times 2 root 3 gives us 6 root 15, and 3 root 5 times negative 4 root 5 is then going to give us negative 12 times 5, or 6 root 15 minus 60. Before continuing, some of you may be wondering how it is that I knew that root 5 times root 5 right away was equal to 5. So let's just take a moment to do a little aside and think, if I have root 2 times root 2, some of you might say, well, isn't that just root 4, which of course simplifies to 2. We can also look at it as root 2. If we were to square it, the square kind of counters the square root, canceling each other out, leaving us just with the radicand of 2. Let's take, for instance, root 7. Root 7 times root 7, some might say, is equal to root 49, but that simplifies to 7, or simply root 7 squared will equal 7. So we can then say that root x times root x will give us x, and because we've just worked with our number sets, we can say that x must belong to the set of natural numbers. Let's look at our last example. So binomial times binomial, and that means that we need to look at doing FOIL. So 3 root 2 times root 3 gives us 3 root 6. Outside, 3 root 2 times 2 root 2 gives us then positive 6 times root 2, or just times 2, sorry, root 2 times root 2 is 2. And then inside, negative 5 root 6 times root 3 gives us negative 5 root 18, and last, negative 5 root 6 times 2 root 2 is negative 10 root 12. Looking at our radicands, we know that root 18 and root 12 can be further simplified, so let's go ahead and do that. 3 root 6 plus 12 minus 5 times root 9 times root 2 minus 10 times root 4 times root 3, so that gives us 3 root 6 plus 12 minus 5 times 3 is 15 root 2 minus 10 times 4, or 10 root 4, or 10 times 2, which is 20 root 3.